Thank you very much for the invitation. I think last time I was here, it was before the pandemic, so I'm happy to be back here in person. See all of you. So yeah, I'm going to be talking about the recent paper we wrote with Luca and Iliesu and Samir Murthy. We wrote two papers, but I'm going to focus on this one, which is the one related to how to count black hole states from the gravitational path integral. Okay, let me start with some motivation. So, near extremal black hole present very interesting features in the spectrum. In particular, as we take the extremal limit and we look at low temperatures, quantum effects coming from a certain gravity mode near their throat, near the horizon, become very large. And okay, let me separate this. And the spectrum we expect them to have derived from gravity is very different from the classical approximation. So in the, let me draw some pictures just to. So this rho is the density of states as a function of the mass. let's say for concreteness, I will be more concrete later, but let's say we're talking about Reisner-Nordstrom in flat space in 4 dimensions. So classically, the density of states will go to a constant as we approach extremality, but once you include quantum effects, density of states actually goes to 0. And this happens at the scale called that used to be called the gap scale, even though there is no gap. And it's roughly of order 1 over q cubed. Well, this is in units of where g Newton is 1. So this is a very tiny temperature scale. But the black hole is anyways big, it's macroscopic, but still there are large quantum effects. Okay, so this is in, let's say, Einstein-Maxwell coupled to matter. But the situation if we have supergravity, let's say half BPS black hole in n equals 2 supergravity, the spectrum is very different. Well, classically it's the same. Classical geometry doesn't distinguish between the two, but when you include quantum effects, the quantum effects care whether you have gravitinos or not, or what type of matter you have. And the answer actually does go to 0 at some, oh, sorry, maybe I should have said, yeah, okay, let me go back here. So the overall scale of this density of states is exponential in the area, which for a Reisner-Nordstrom black hole is exponential in q squared. So this is, q is the size of the horizon, and this is the area.
This 1 over q cubed is in time units, right?
Yeah, so it's very tiny. It's of order g Newton, or, yeah. So it's power law suppressed in the entropy. And now we have a gap that is at order, well, not order, actually one can compute it, and is 1 over 8 q cubed, where now I put the 8 to show you that I know what that number is, but it doesn't, I mean, it's just an order 1 number. And then you have a delta function. One of the surprising features is that this delta function that counts the number of BPS extremal states can be seen from a gravity calculation, including this gap and this. So let's say this is for half BPS in n equals 2 supergravity. So one can ask several questions about these near extremal black holes. The first question one can ask, that I'm not going to discuss in this talk, is what is the gap, as I said. For example, here, the gap is power law suppressed in the entropy. And in this case, the gap will be exponentially suppressed because this is a continuous function. But of course, we expect non-perturbative effects to eventually resolve this continuum into a discrete. And if the spectrum is chaotic, we expect the energy level to be separated by exponentially small gaps. But the question that we are going to be interested in is still, so okay, the first question is the gap exponentially suppressed or power law suppressed? But the question that we're interested in is whether we can do better about counting this delta function here. So to leading order, this is exponential in the charges. But for example, something that this doesn't show, if we assume that this black hole is described by a quantum system, is the integrality of this degeneracy. So the purpose of the talk will be to show in some examples from string theory where we can do the path integral that computes the coefficient of this delta function exactly, and see how we obtain an integer and match that integer with the quantum mechanics that appears in the deep brain construction of these black holes I will describe. Yeah.
Sorry, when you say an example from string theory, you're not using string theory, right? Just to confirm it.
Yeah. So I mean that we will match with the countings in string theory. Well, this string theory is just a tool that will tell you that these black holes, what is the quantum system to associate to these black holes. And
Wouldn't we have known that from supergravity already? Invent strings for that.
yeah, how do you? I don't know. Like if I give you like type 2b whatever supergravity in ADS5, how do you know that it's n equals 4 super Young means? That's the dual. That's.
You're not going to use this stuff. I thought you were going to use the gravitational value. You're just using the bulk.
No, I just meant to say that it will match. I'm not going to do anything with that system other than just telling you that it matches with whatever you get from that approach. Yeah.
So you're going to do the calculation 2 different ways, right? One with using string theory, one using the gravitational path integral.
Yeah, I will do the calculation using the gravitational path integral,
Okay.
and then I will just claim that that's the same as you will get from doing the counting with Libre. Because this was something that people already did. I mean, it's just something that people already did. Like, I'm not going to repeat it in front of you, but.
So with ADS, you would not be able to do this, right? You would not know how to get an integer.
No, at least not in any example I know of.
Yeah.
I mean, presumably what I can do is.
So what you're doing is like a million times better.
Yeah, maybe. I mean, like. Okay, in ADS-CFT, one example is, okay, all the countings in string theory were done in flat space, 5D, 4D flat space, and only recently, maybe in 2015, the first countings in ADS were done in ADS4 by counting in AVJM, and it's just that the countings to be done from the quantum mechanics side on the boundary are much more complicated than the one in flat space. So that's why I guess it took longer. And then after that, also people figured out how to compute the degeneracies of black holes that are BPS on ADS5. So maybe one can repeat this in ADS, but I'm not going to try to do it. I will just do the flat space.
Well, just to keep pushing against you,
Yeah.
you're selling your work.
Yeah. No.
I mean, all of
Yeah.
these examples were not, they were arguably not counting the states of a black hole. They were,
Yeah.
they were computing the index
Yeah.
of a weakly coupled system that you could argue might have the same number of states as the black hole.
Yeah.
But that argument wasn't even completely bullet.
Yeah. Well, first of all, something you can do in gravity is to compare indices with indices. You can compute the index in supergravity and compare the index without asking.
Yeah, exactly. But that's actually not the thing you're interested in. But you can also
Well, we are interested in both, right?
okay.
Yeah. So we will. The way we will do it is to compute the index in supergravity, and then we'll give an argument that the degeneracy is the same from supergravity. So then the degeneracy could be the same at weak coupling, but then when you go to strong coupling, it should be the same if it matches with the black hole. I mean, that's something that will be hard to see from the quantum mechanics directly. But
Can this be done for any n equals 2 supergravity?
no, actually, I will do it for n equals 8. Yeah, sorry. The reason why maybe let me continue and that will be clear. Yeah. Sorry, I just wanted to draw this picture to make sure that we're in the same page with these things. Okay, maybe let me say it. So we will do it for 1/8 BPS black holes in n equals 8 supergravity. So the reason that I mentioned n equals 2 is that this preserves the same supersymmetries as a half BPS black hole in n equals 2. So I will use an n equals 2 language, even though I will apply it to n equals 8. Yeah.
just like n equal 8
In 4D, yeah. Okay, so let me continue. So yeah, so from string theory we will do. Was there any? Oh no. Okay. We will do type 2, compactified on T6. So this is the 4-dimensional flat space where the black hole lives, and here is where this n equals 8 supergravity that appears from doing this toroidal compactification. Let me mention that this theory has 28 electric charges and 28 magnetic charges, and then they combine into one vector. Let's call it QA, where A goes from 1 to 56. And the motivation to define this vector of magnetic and electric charges is that this theory has a symmetry that is, okay, this, I'm not going to go into too much detail, but it's called E77. And this is a generalization of a duality that rotates electric and magnetic charges. So that's a symmetry of this theory that was found out by Kremers and Julia, long time ago. In this theory, one can write black hole solutions that are roughly Reiser-Nordstrom with some scalar profiles. And then one can compute the entropy of these black holes. In the classical approximation, this is given by the area over 40 Newton. Let's call it Bekenstein-Hawking. And for the black holes in this theory, they are given by this formula, where delta is some, let me write. So basically here, delta is something that is quadratic in the charges. And I'm not going to tell you what these coefficients are, but there is a unique choice that is consistent with this E77 symmetry. So these are known, is a known invariant under this duality group, and the entropy depends only on this coefficient delta by this duality. And the gravity picture, if we look at the black hole, then the gravity picture is accurate in the limit that delta goes to infinity. And again, we are looking at fixing in units of Planck length. Yeah. So on the microscopic side, where microscopic I mean using this quantum mechanics from the D-branes, this can be thought of in different frames. So one in type 2b, this is a system of D1, D5 Kaluza-Klein monopole, are in type 2a. This is a D0, D2, D4. And we will actually use the type 2a frame, and this D0, D2, D4, the way they appear in 4 dimensions is that the charges will be under some Ramon-Ramon fields corresponding to D0, D2, D4 branes wrapped on T6. So that's the setup. But the counting is usually done in type 2b, where you have the D1, D5 brane system, which is a black hole in asymptotically flat 5D space, and then that put on the center of Kaluza-Klein monopole to make it effectively 4-dimensional. The calculation we will do in this frame. And then these black holes have a ADS2 × S2 horizon. Let me write the answer from string theory, from like the microscopic approach, let's say. I will write W, which is the index of these black holes, and up to some numerical prefactors that I'm not going to write is given by this formula. It's a sum over some integer C. This is 0.5. So this is what it is. So it's an integer that amazingly can be written in this way. This is a sum over an integer C that goes from 1 to infinity. This is just a prefactor. This is a Klosterman sum that is I'm not going to write down, but, well, I can tell you that it's a sum over some other integer D that will appear later that goes from 0 to C, just that is coprime with it. But the only important thing is that it's a sum over phases. So this is a sum of phases that you can write down. So it's kind of long to write down, and it won't be. I'm not going to go in detail into these phases, but they're part of the final answer.
So index means weak index?
Huh?
Index means weak
Yeah. Well, okay. There is a small subtlety. These are usually Helicity supertraces because if you look in flat space, the Witten index is 0 because there are fermion 0 modes from the translational modes of the black hole because of the broken supersymmetry. So, but once you extract all the modes that come from the exterior of the horizon, this is the index of the black hole states. Yeah. But if you look at it in the asymptotically flat space, this is a Helicity supertrace. Yes. It's just okay. So the question we want to ask is, can we reproduce this exact answer from gravity? And here it's important that you see that non-perturbatively, the answer is only a function of delta for any delta. So this will be important later, the fact that this index cannot depend on all the charges independently. It has to depend on this duality invariant combination. Okay. So before I tell you how to do it, let me try to guess from this formula what the macroscopic interpretation could be, where by macroscopic I mean black hole plus corrections. Put a question mark for later. So first of all, if you take the delta going to infinity limit, then W is approximately e to the pi square root delta minus 2 log delta plus dot dot dot. So this reproduces the Bekenstein-Hawking part that I wrote before, and there are also log deltas that are quantum corrections. They can be reproduced by doing a one-loop calculation around these black holes, and this was done by Ashok Sen and collaborators, and they get the -2 on the nose, so it matches with both sides. And this comes from looking at the large delta contribution of c equals 1. Then this Bessel function, it's exponential when the argument is large. So that's where it comes from. So then it's reasonable to believe that for c equals 1, this should be thought of as the original black hole with some quantum corrections around it that happen to give this Bessel function. And we will see that this is how it works. I'm just trying to tell you from looking at the formula what we expect, but we will see that that's how it works. So then you can ask, so this gives an interpretation of what, I didn't tell you how, but of what the c equals 1 contribution might be. But then the total answer is let me write it this way, over c over c. And here this WC is this term that appears there. And this WC, if you expand it at large deltas, it will behave in this way. So it's the same entropy as before, down by a factor of c. And what this indicates is that it's very natural to expect this contribution to come from an orbifold, because it's the same as the black hole, but this 1 over c you can interpret as a volume. Just the volume of the space-time is smaller. Yeah.
You're now talking about macro picture.
Yeah.
Classical space-time.
Yeah.
Is from low energy, that point of view, is there E77 is an input?
E77, well, once I tell you that it's n equals 8 supergravity, that's the symmetry of the theory.
You have to impose that?
It's just the symmetry of the Lagrangian. I don't know. Are you asking quantum mechanical? It's a symmetry of the Lagrangian, yeah.
Okay, it's a standard symmetry.
Yeah.
It's there.
It's a what?
It's there.
It's there, yeah, yeah.
It's not in.
No, it's there in the low energy action. I mean, you could ask if that should survive quantum mechanically, right? Maybe the measure, or maybe quantum mechanically you can break it, but it doesn't happen. I don't know. It happens to be an exact symmetry. Yeah. Yeah, okay, I'm not going to write the reference, it will take me too long, but yeah, that was pointed out by Kremers and Julia a long time ago, and then this formula for the black hole entropy was by Svietich and Hume, and also Kalosh and maybe other people. All right. Okay, so this indicates that, so the upshot of the calculation I'm going to describe is that this is a sum over different configurations where each of them is an orbifold of this extremal black hole, and we will reproduce these Bessel functions by looking at quantum corrections around them. And I won't have time to explain this Klosterman sum that appears here, but that comes from looking at some non-trivial topological sectors of some gauge fields. So if you compute the action a little more carefully, then you'll get the right phases. But this was done by Doublecard, Murthy, and Gomez. Okay. Okay, so now I'm going to move on to discuss how to do this path integral. So we're going to use localization, so I will give a short summary of how to do localization in supergravity. Is there any question before I start with that? Okay. Okay, so we're going to use a formalism. So there is no official formulation of n equals 8 supergravity, so we are forced to go down in supercharges. So we are going to use a formalism with n equals 2 supergravity, adding some number of hypers so we have hypermultiplets and vector multiplets. And actually we also have, well, besides the graviton multiplet, and also we will add later gravitino multiplets. These gravitino multiplets are the ones that are going to extend the supersymmetry to unequal state. Yeah.
Like super, is it two derivative?
No, actually we will include all derivatives, but there is something, okay. I'm going to find the localization manifold, and then on that you have to compute the action. That action is sensitive to higher derivative corrections, but in n equals 8 there is, if you have n equals 2 you always have f and d terms. The f terms are not sensitive to higher derivatives because of the supersymmetry. The d terms are, but when you evaluate them on these solutions they are 0. Basically because they're the ones that are integrals over the whole, all the superspace coordinates, while the f terms are kind of only over half of them. So in supersymmetric configurations, the d terms are all vanished. So all the higher derivative corrections that come from stringy effects, they are there, but they just not contribute. They don't contribute in this particular calculation. So that's a. But if you go down in supersymmetry, then higher derivatives contribute also to f terms, and then you have to. So this is one of the reasons to restrict to n equals 8, because we know exactly what the action is. Yeah. So
when you were discussing the microscopic derivation using p-branes and so on,
yeah.
I mean, there wasn't any particular reason to write the integer answer in terms of this Rademacher expansion, right? It was just like, you can.
Yeah.
And then the game is basically try to match every term
Yeah.
in the gravitational path.
Yeah, that's the. Yeah, actually it's usually done a little different. Like if you look at the papers, the formula is given in the grand canonical, where instead of fixing charges, you fix chemical potentials for the charges, and then the answer is some modular form, weak Jacobi modular form, whatever. And then the Fourier, the Fourier coefficients of that modular form give you the index at finite charge, and then this Rademacher is what you would get from extracting the index at fixed charge from those formulas at fixed chemical potentials. Yeah.
You have to somehow notice that it's the right. So the integrality is manifest in that calculation. Right?
Yeah.
And you have to sort of stand on your head to make it look like a funny sum of things that are not interesting. But
well, not. I don't know. It's kind of like the partitions of these PNs that we were talking before. So there are some certain things whose generating function is easier to write than the counting directly. And this is one of those cases. The grand canonical is easier to write, but then if you want it at fixed charge, you need to do some extra work, and then that gives you the Rademacher expansion. Even if you don't care about gravity, just computing those.
I mean, you could imagine that you do a calculation of the integer number of states, and the numbers just don't come out to be the kind of numbers that you can expand this way, right? So that was
yeah. So that's a consequence of the fact that this grand canonical partition function is a modular form, which didn't have to be that way. And maybe what I cannot answer to you is from gravity, why should that have been the case? Why should that have been a modular form? I don't know. So that plays a role into why I can even write this expression.
Yeah, I mean, that's what makes it suggestive that there should be some other way of deriving it where you use that expansion.
Yeah.
It didn't have to happen that way.
Yeah, but I don't know. Yeah. But something similar happens for the black holes in ADS, where you can write the grand canonical one for the index, but then if you try to compute the degeneracy as fixed charge, then the thing is not a modular form, and there is actually no exact answer that I know of. So there is something special about these ones that you can write so easily as a Rademacher. Yeah. Okay. All right, so n equals 8 can be expanded in this set of multiplets of n equals 2. I will tell you more details later. And in general, we can have electric and magnetic charges where this index lambda goes from 0 to NV. 0 corresponds to the graviphoton and NV to the NV vector multiplets. And in principle, one can also have charges from the gauge fields that appear in the gravitino multiplets. There are U1 gauge fields there, but we'll set them to 0 because otherwise I don't know how to do the calculation. Basically, they mess up the n equals. They mess up the way to write n equals 8 as n equals 2 in n equals 2 language. So we are going to restrict to that case. We want to perform the path integral we will assume that we can perform it near the horizon, and we can ignore the things that are outside of the horizon. This is an assumption that roughly goes under the name of the quantum entropy function of Sen. Basically, what it means is that we'll do the path integral on a space that is asymptotically ADS2 cross S2. So these are our boundary conditions. So this is the boundary of ADS2 cross S2 that should be glued to some asymptotically flat region. And this is times the sphere. And okay, I don't have time to explain it in too much detail, but as I said, we want to compute indices with indices first to make it as accurate as possible. So we don't have to discuss whether index is the same as degeneracy at this level. We can discuss that later. And to compute an index in supergravity, what you have to do is to insert an angular velocity that is 2 pi I over beta. Yeah. So we want to do the calculation with boundary conditions that the black hole is rotating with this imaginary angular velocity. And this has the effect of implementing in the putative quantum mechanics. If it's a trace where you insert some angular velocity, so you insert this operator, then this implements the -1 to the f, roughly. So it's a way to implement it in gravity. If you add rotation, you can compute the index in a solution that, if you would impose the equations of motions, is smooth and yeah.
So here you have to work harder to get the index. And you have to stick this in.
In a sense, it's better because the calculation with the extremal black hole is kind of there is some problem from the fact that you have the horizon goes to infinity at 0 temperature. So actually, it's good to turn on temperature because it regulates some divergences in the one loop determinants, because now the horizon is at a finite distance. So this is actually good even to. So all these calculations.
I thought.
Yeah.
I'm misunderstood.
Yeah.
I thought you were just trying to put something in that ensures that you end up computing an index as opposed to computing a number of states.
Yeah. I'm just saying if I want to do the path integral at exactly 0 temperature, then there's a singular limit because the horizon is infinitely far in a sense.
You should be able to compute both the index and the number. Well,
yeah, but it's always better to do it at finite temperature and then take the 0 temperature limit in the end. Then you can get to confusions like, well, for example, there was a paper in the 90s by Horowitz, Hawking, and Ross saying that the entropy of the extremal black hole is 0. That's kind of, yeah. If you do a calculation at finite temperature and then take temperature to 0, then you wouldn't run into this funny.
so what would you do if you wanted to compute the number of states?
Oh, no, then I wouldn't turn on omega. I would do it at finite temperature, but I wouldn't be able to apply localization because I'm using boundary conditions that break supersymmetry.
You'd only be able to apply localization in the limit when t actually goes to 0.
Yeah, but that's kind of a singular limit, so okay.
What happens when you take that limit?
You still
Well,
get an
yeah.
answer that's consistent between the degeneracy and the index. You still manage to say that the degeneracy is equal to the index.
Yeah. Just prefer that to separate the discussion into, I'm going to apply localization, so if I tell you I'm using localization on a system where I'm putting boundary condition where I break supersymmetry, I wouldn't trust it to begin with.
So if you formally do the calculation anyway, you get an answer you like, but you don't have the justification for why it's right.
No,
Yeah,
you have
well-
the justification in the limit t goes to 0.
Yeah. But I didn't tell you what the justification is yet. So that's a further argument. But if you compute the index, then you can use localization, and then you're going to match with the index from the string theory formula.
I guess Joaquim's point is that this is more general because you can do the computation at absolutely any beta.
Yeah.
And you still get the right answer.
Yeah.
So it's a very general check.
Yeah.
Okay.
When you say right, what does it match?
What do you mean? Sorry,
When
what?
you say get the right answer at finite temperature, what do you match?
Well, for example, if you compute the action on this rotating black hole, you'll get an action that is independent of temperature, and it gives you the extremal area over 4G Newton. So it picks, at any temperature when you compute it, because it's an index, it always picks this delta function. Yeah. Well, if you don't put supersymmetric boundary condition, the answer depends on the temperature, for example, of course. Yeah. But I'm going to do localization, so if I break supersymmetry, then I don't know how to justify it to begin with. Okay, is that clear?
Sorry, are you going to do two calculations? Are you going to compute the index and the partition function?
Well, I don't think I will have time, but
you can do both as well.
you compute the most rigorous one is for the index, and then you can argue that all the other contributions that appear in the partition function, when you take the zero temperature limit, they all vanish. Yeah. For example, I don't know, if you add like a wormhole on ADS2, even if you have a supersymmetric theory, you compute the partition function, that will be a contribution that will go to zero at zero temperature. So then the two calculations will match. Yeah. So that's what Luca was mentioning. But that's I prefer to think of it as an afterthought of this calculation, because if you have if you break supersymmetry, then how do you do localization? Yeah.
So, I mean, the sort of slightly problematic assumption in the string theory calculation, right,
Yeah.
is that you could only compute the index.
Mm-hmm.
And so you had to assume that there's not some major cancellation between the bosons and the fermions, right?
Yeah.
You don't have to make that assumption.
No, from gravity, no, because one of the points that was only understood in the past years, with the help of this ADS5 story also, is that you can also compute the index in gravity. And then okay, I think now we were talking about exact statements, but you can talk about semi-classical statements. Semi-classically, the calculation for the index is different than the one for the degeneracy, and they both match. That's the result, even though this one has rotation and the degeneracy will be without rotation. They both give the same answer, which is the area over 40 Newton. So then gravity also tells you that there are no cancellations.
But this is at a level where you're not getting an integer.
Yeah, but then now we will add, And let me see. Then another thing is that when you do the quantum mechanics of this strongly coupled mode close to the horizon and you solve it, it tells you not only that you have a delta function, but that it has j equals 0. So you only have bosonic states. This is from gravity. This is a gravity calculation. The same calculation that tells you have a gap tells you that all the ground states have 0 angular momentum. So then there are no. This is a more precise version of what I just said, that there are no cancellations in gravity. But before this was assumed, but I think now we understand how to use the Euclidean, like a Gibbons-Hawking prescription to compute the index as well. So then you can see it.
So you can, sorry, this seems important to me. So
Yeah, no, I agree.
So you can make the following argument, right? That you have complete control over the index calculation in gravity.
Yeah.
And you also have complete control over the argument that shows that there are no cancellations at all.
Mm-hmm.
And then you can just say, well, therefore the degeneration.
Yeah, that's what Lucas said before. Yeah.
Thank you.
Yeah. Okay. No, that's fine. Yeah, please ask question. I mean, I guess if I don't finish, I prefer if we prefer to have these discussions than going over it quickly and then, no, yeah. Sorry, what?
Sorry if you went over this already, but
Yeah.
how do you calculate the index using the Gibbons-Hawking prescription?
It's this argument that you should think that you're inserting -1 to the f as turning on some imaginary angular velocity, which is actually real in Euclidean. So if you partition function is an Euclidean object, and in Euclidean everything is real.
I see, you're saying that 2 pi rotation is -1 pi rotation.
Yeah. So the fermions are periodic in time, but that's not incompatible with the time with some cycle being contractible at the horizon, because the actual contractible circle is a combination of time and the rotation angle. And then the fermions are anti-periodic with respect to the actual circle that is contracting. Yeah. So that's the idea of these gravity calculations of the index. It's the same principle that people use in ADS5 black holes in this 116 BPS calculation.
Sorry, just to make sure I understood.
Yeah.
Localization works at finite temperature for the index.
Yeah.
But it doesn't work at finite temperature
For the partition. Yeah, exactly. Because for the partition function, you're putting boundary conditions that break supersymmetry. So, yeah. Well, also the bulk breaks supersymmetry. Everything. But, yeah.
But everything's okay when you take t to 0.
Yes, but
It's a singular limit.
it's a singular limit, so I prefer to do it this way. Yeah. Okay. All right. Okay. So here the idea of localization is to pick a supercharge related to the asymptotic Killing spinors of this geometry that squares to, well, we will pick it such that it squares to L naught minus J naught, where L naught are, well, if we will write ADS2 everywhere, they are rotations around the Euclidean horizon, and J naughts are rotations around a certain direction in the sphere. So this just tells you which supercharge you use. And then you take the action in supergravity, and you add a QV term, where this V is some potential that you can write, you can choose. You're kind of free to choose this, because as long as this modification has this form, Q of any V, the answer will be invariant, and it will be independent of lambda. So you can evaluate it that lambda goes to infinity. And this tells you that you only get contributions from configurations that are supersymmetric, but not necessarily on shell. So we can look at what localization buys for you is that you can reduce the infinite dimensional path integral to a path integral over configurations that preserve this Killing spinor, but they don't need to solve the equations of motion necessarily. So they're not just shadows, but they're way less than the most general fluctuations. B, you have to choose it yourself. It's like that's part of the art of localization. You need to find a good one that's what you want. But usually V is a sum over all the fermions, and it has this form. This is a fermion, and this is Q acting on the fermion. So when you add with Q, you end up with like cube psi squared, roughly. This is sum over all the fermions. So then when you take lambda to infinity, you restrict to configurations where QV is 0, and those are the ones where the fermions are invariant. And yeah, so that's usually how it goes. Okay, and the simplest configuration that preserves supersymmetry is ADS2 cross S2 itself. So let me write it down. The metric. Here rho is the radial distance, and rho equals 0 corresponds to the location of the horizon, and large rho corresponds to the boundary of ADS2. And then we have S2. So this is S2, and this is ADS2. But then here in n equals 2 supergravity, we also have scalars coming from the vector multiplets, and they're usually not. They usually run in the radial coordinate as a function of the radial distance outside of the horizon. But if you look very close to the horizon, then they take a constant value, and this constant value is independent of whatever boundary condition you put at asymptotically flat space. And this is what's called the attractor mechanism, the fact that these scalars take values that depend only on the charges and not on the boundary conditions. And I'm not going to write it down, but this P lambda are the magnetic charges, and E lambda are functions of the electric charges, E star. Okay, but these are the classical, these are solutions of the equations of motion actually, but if you impose just that the solution is supersymmetric and not the equations of motions, that leaves you some extra degrees of freedom that we can write parameterized this way. So this was done in a paper by Dabholkar, Murthy, and Gomez. So you can see that this phi, when phi is equal to E star, then this vanishes and you are on shell. But if phi is different than E star, then you can see that this is a solution that, okay, it's hard to see, but it's supersymmetric. Well, I didn't tell you what cube psi is, but if I would, then you'll see that it's supersymmetric. But the point is that this vanishes at large distances. So if you take rho to infinity, this goes to 0. So if we work with boundary conditions where we fix the scalars to their attractor value at the boundary of ADS2, then these are configurations that are supersymmetric, are not on shell, but satisfies the boundary conditions. So the localization manifold is parameterized by NV plus 1 coefficients that are this phi lambda. And you can think of them as the value of this, sorry, this is the scalar in the vector multiplet, so you have as many as vectors. And yeah, so this 5 lambda, you have NV plus 1 of them, and they parameterize the localization manifold. So here there is some subtlety. Usually in the off-shell formulation of supergravity that we use is conformal supergravity, and then we gauge fix to what's called Poincaré supergravity. And that gauge fixing can be done in different ways. The way we do this here is a little bit unnatural, which is we fix the overall scale of the metric to be 1. If you see there is no overall ADS2 scale here, just 1. But the scale of a metric appears as an extra scalar, is this +1 here. So the scalars are the partners of the vectors in the vector multiplets. Lambda equals 0 corresponds to the graviphoton, but the graviphoton has no scalar because that one is in the graviton multiplet. So the +1 here, you should really think of it as a mode describing the physical scale of the metric. And one way to see it is that when you use this funny gauge fixing of the conformal gravity, the Einstein term in the action becomes this, so it has an overall factor. And if you compute it in these solutions, well, let me tell you what it is first. Okay, yeah, so the ADS2 scale, the physical ADS2 scale is given by this parameter e to the minus k, where k is given by this equation. So you take x, the scalars in the vectors, f is the prepotential, which is a function that characterizes these f terms that appear in the action, so it's part of your definition of your theory. And then you compute this, evaluate it at the horizon, and that gives you the ADS2 scale. For example, this is proportional to the Wittgenstein-Hawking entropy. Okay. All right, and then you have these orbifolds that I mentioned. So the orbifolds act in this way. So in this solution, we have tau goes to tau plus 2 pi are identified, and psi goes to psi plus 2 pi are also identified, where psi is the rotation angle of the sphere. Yeah.
What you're doing now is it's finding all the solutions that satisfy Q psi equals 0,
Yeah.
and then you're going to add them all up.
Yeah. Yeah. And then I will, well, if I have time, I will show you that it gives this Bessel function. Yeah. So what I told you so far will reproduce the C equals 1.
This is still it's still a continuous manifold.
Yeah.
It's just much less
Than the infinite dimensional path integral. Yeah, and also it has an advantage that the metric is always, in this gauge, where we fix conformal supergravity to Poincaré, the metric is fixed to be ADS2 cross S2, and all the degrees of freedom of that localization manifold are in the scalars instead. So that also simplifies the problem. So all these finite dimensional integrals are just parameters of the value of the scalar is just allowed to fluctuate, but other than that, you have ADS2 cross S2 everywhere. Well, yeah, I will say no. Yeah, so far it's C equals 1. So okay, the quotients can be obtained by this same metric with this change in the identification. So psi, the rotation angle, is still identified with 2 pi, but tau is identified in this way. So now the size of tau is down by a factor of 1 over c, and as we go around tau, the Euclidean time, we rotate the sphere by amount 2 pi over c. So this is the orbifold we consider. And from the point of view of ADS2, this identification, if you forget about the rotation angle, you're just identifying the Euclidean time with the wrong period, so you will have a defect on ADS2. So the metric will be, okay, the same sphere, and then ADS2 with some defect. And this is the angle of the defect. So then one question you could ask is okay, if this configuration is singular, then why should I, okay, I didn't tell you yet, but if you compute the partition function, the integral over this localization manifold and these geometries will match with the different values of C in that Rademacher expansion. But you could wonder why should I include this configuration because it looks singular, right? And the answer is I don't know, but if you want to reproduce the index, you should include it. But there is an argument that I think is very useful, which is that you have to remember, okay, I didn't tell you, but you have some sum over other integers in the Klosterman sum. And some of those integers correspond to adding holonomies on the gauge field. For example, this D. So we have a gauge field, and the D will appear in the gauge field that corresponds to the D0 charge in type 2A. So it's like a Ramon-Ramon gauge field in 4D. This has some value. Let's say C equals 1. At C equals 1, it has some value. And then you should also allow for non-trivial holonomies around this thermal circle. So here I am adding a singularity in some U1 gauge field besides the singularity in the metric. So then you think, oh, didn't you make the problem worse? Just added 2 singularities. But if you look at this in strong coupling, where this type 2A becomes M theory, then this gauge field, the charge of this gauge field corresponds to momentum along the extra M theory circle. And then the geometry, so basically you have ADS2 cross S2 cross T6 cross S1. So this is the 11D circle. And if you look at the geometry in this part of the space, this is the near horizon limit of a BTC black hole with a modular image of a SL2C black hole. And this is actually smooth. So something that is, so my point is that from lower dimensional perspective, this configuration looks singular, but it's actually smooth in higher dimensions.
So
yeah.
you have, I mean, so here you're kind of borrowing some result from string theory in the sense that you
Yeah, you could say that, yeah.
Could you have avoided that by somehow just working in 11 dimensions from the start?
Yeah, I guess it's just, yeah, that's a good point. It's difficult. It's difficult to decide in 10D what singularities to allow or not.
Yeah.
So.
Would there be an obstruction to just carrying out the entire analysis? 11D school gravity.
Yeah, I think maybe what you're asking, or maybe what you might be asking is if I can have any argument within 10D that would tell me that this is smooth without having to go to higher dimensions,
No,
roughly.
without having to
So I don't have to talk about M theory.
So,
Yeah.
I mean, I'm confused whether can I just think of, I don't remember how this works, but can I just think of the type 2 school gravity that you're working in as
Yeah.
as a dimensional reduction of some 11-dimensional theory?
Yeah.
Without reference, again, without reference to specifically any string dualities. And use that to argue that everything is smooth here.
Yeah, that's kind of what I'm doing.
Oh, I'm sorry.
Yeah.
So there's no, okay.
Well, I'm using the fact that a strong coupling type 2A is really M theory in one more dimension, but.
Yeah, that's kind of a straight argument.
Yeah. Or are you saying if I start in 11?
That connection, for that connection, you need string theory.
Yeah. But yeah, so the only input here is, but I'm not using it in the calculation other than to decide whether I want to include this or not. So that's
But I think it's very interesting to ask, how much of this could have been done just,
yeah.
in some other history where all you do
Yeah.
is applying the gravitational path in the
Yeah.
world, and nobody discovered all the string theory
Yeah.
stuff yet.
Well, I think probably you could say, okay, it's a binary choice. You include it or not. If you don't include it, you will get some nonsense. If you include it, you get the integer.
Well,
So
there are a lot of singular contributions you would have to,
yeah.
There's
Okay.
an infinite number of contributions like this that you could in principle consider.
No, that's true. Yeah, you're right. That's true.
I don't think this
yeah.
infinite number of contributions that are singular necessarily all contribute to the infinite.
Mhm.
Right? Because there's an additional constraint, which is that the entire manifold needs to have killing spares, right?
But within the supersymmetric ones, there also might be other orbitals.
Yeah, that was
Besides
my
the
question,
one,
whether
yeah.
there's something similar
I mean, in principle, yes, but
But you don't know an example.
I don't know.
That was the
Yeah,
question.
I don't know.
Like,
Yeah.
whether there's an example, like
Yeah.
similarity, weak similarity, but should
Mhm.
not include it. You don't have that example, so it's possible.
Yeah, I don't know.
Everything should be just be included, consistent with the orbits.
Yeah.
Requirement of the-
Yeah. I'm not sure. Like, I cannot tell you an explicit example of another configuration that is supersymmetric but shouldn't be included. But in principle, there could be. I don't know.
But
Yeah.
in principle, that might not exist.
That might not exist. Yeah, I'm not 100% sure.
Yeah.
Yeah. Yeah.
still need any.
Yeah.
Right. So that's.
Yeah, if you somehow can show that, well. Well, I guess a stupid one would be like, this is supersymmetric as long as you do the same rotation on the S2 as, for example, these shifts could be unrelated in principle, the angle of the orbifold and the rotation on S2. And this is supersymmetric only when these two angles are the same. Okay, but then maybe you could imagine that C is not an integer, it's a real number. And then that one I'm not sure how to rule out. Other than...
Well, then, are you claiming that's an example?
I think that's an example, yeah. Because it's important, okay, yeah, sorry, I think, okay, I definitely won't have time to finish, but it doesn't matter. One way to see that it's smooth is that if you have this orbifold and you have this extra circle, this is the M theory circle, when you go around the orbifold, you go around an amount 2 pi over c, that's the origin of the defect. But then what this holonomy tells you is that you move along the circle an amount, well, 2 pi d over c, roughly. So then the reason why this is smooth is that if you go c times around this conical singularity, so that you go around it a total amount 2 pi, so that ADS2 is you're back to where you started, you'll go back also to the place you started on the extra circle. Okay, so this is smooth because of that, and well, another way to say it is that as you go around here, you don't have fixed points because this would be a fixed point if yeah, this is not a fixed point because of this extra translation you're doing in the extra circle. But if D would be a continuous parameter, then I'm not sure what to make of it. But I don't know. Yeah. Yeah.
You can't make this argument without introducing this extra circle somehow, right?
Yeah. I don't know how to make this argument without the extra circle. Yeah. Even if I could show that there are no other configurations, I would still like to know how to show that this is. Let's say there is no other supersymmetric one. I would still like to know how to argue that this is something you should include, other than the fact that it exists and I write it down. Yeah.
This is where all the number theory stuff is, like where.
Yeah, for example, this Klosterman phase comes from computing the action of supergravity, being careful about this, the fact that these holonomies are not trivial. Yeah. And there are other integers there that correspond to other shifts of other gauge fields. And I'm not saying just so I don't, just because I don't have time, but yeah. Okay. Any other question? Okay. Okay, let me write the final answer for a general n equals 2 theory for the index for some orbifold C. So then the final answer is an integral over these nv plus 1 directions. And here we have to decide what measure we're going to use for this integral, but I can mention the result. We have a one loop. And this is, sorry, some of the things I did, some of the things I mentioned were done by Doublecard, Murthy, and Gomez. But something they didn't do, which was the main thing we did with Luca, was to compute these one loop determinants explicitly for all values of C. Because if you don't compute the one loop determinant, you cannot really justify that you get that formula and not something else. So that's the thing we added to this story, I would say. Yeah, so then you have the one loop determinants, you have these Klosterman sums that depend on delta. Where this Klosterman, okay, I'm not telling you, but they have been matched to terms in the action. And then you have the rest of the Euclidean action, which is, let me see, to the cube 5. Okay, so maybe let me write it here. Okay, so this is the action evaluated on this localization manifold. Q are the electric charges, phi are the coordinates of the localization manifold, and this is the imaginary part of the prepotential, which is a function that characterizes the theory. It's just, if you try to write down the Lagrangian, you give me a function, I write you the Lagrangian for n equals 2. And this is well, this is the answer which, after you plug in the one-loop determinants and the prepotential, will give you the Bessel function. So in the last 5 minutes or so, maybe I can tell you quickly how that works. So at least just to finish the logic. Well, okay, of course I didn't say it, but at the end of the day, you need to sum over all this C. Okay. So before I do it, let me tell you more details about how the n=8 supergravity decomposes in n=2. So in n=2 language, this theory has 15 vector multiplets. So this localization manifold is 16-dimensional. That's just the number that comes from this decomposition. It has 10 hypers, and I didn't mention the hypers at all. And yeah, that's important. If you look at the localization manifold, they don't constrain the hypers at all. The hypers can have, the scalars in the hypers can have any value you want, but it has to be constant. But in particular, that implies that if you fix the values of the hypers at the boundary of ADS2, then they will take the same value. They are fixed by the boundary conditions. That's not true about the scalars in the vectors, because the supersymmetry allows you to have radial dependence that satisfies still the boundary conditions. Okay, so this should be thought of as in an ensemble where we fix we put the Dirichlet boundary condition on the hypers. Okay, let me. Okay, so besides telling you how many vectors and hypers, I need to tell you and I forgot, it also has 6 gravitino multiplets. So you have 2 gravitinos from the n=2 graviton supermultiplet, but then you need another 6 to make up the 8 of n=8 supergravity. So that was also another part of the calculation with Luca, because some of the one-loop determinants were computed, but not all of them, in particular not the gravitino ones. So it's important to add them. Even if they don't play a role in determining the localization manifold, basically everything goes in the one-loop determinants. Everything contributes. So you need to know the answer for all of them. But okay, then the only thing you need to know is this function f that describes the action, the low energy action. Or at least it describes the f terms. Then there are other d terms that we don't know how to write them, but they are expected to vanish on these localization manifolds. But okay, for this theory, in string theory, this potential has the following form. Well, whatever, it's the same. So here, I, j, k go from 1 to nv. So this one doesn't include the x0, and the x0 appears in the denominator. And these ci, j, k are the intersection numbers of T6. Yeah. And this is a 3-level string theory calculation, and in principle there can be corrections to this potential, but when you have toroidal compactifications, all the corrections vanish. If you have n=4 supergravity, then there can be a one-loop correction here, and if you have n=2, you can have anything, perturbative corrections. And this is what's computed by the topological string and leads to this OSV conjecture. But anyhow, we don't have to worry about that with this amount of supersymmetry, so that's good. And then we're also considering the following set of charges. So we put arbitrary electric charges. Again, Q0 and Qi, I goes from 1 to NV. Then we're going to consider 0 magnetic charge for the D0 gauge field. In string theory language, this means no D6 branes. And it just simplifies well, I don't know how to do the calculation with D6. So that's what I wrote there. That's why we restrict to D0, D2, D4. Yes, and okay, I said it before, but we are not going to turn on any charge for the gauge fields that are in the gravitino multiplets, because those ones spoil the n equals 2 right enough. They spoil this n equals 2 treatment of n equals 8, basically. Then this invariant that appears in the entropy of the black hole can be written in terms of these charges more explicitly. Well, these CIJK are the same intersection numbers of T6, and this is the inverse. Well, this is the inverse of CIJK PK. Okay, so these are all explicit expressions. And then, okay, I guess I have no time, but let me.
So basically, you analyze everything n equal 2 language.
Yeah.
Then you go back to the original n equal 8 situation,
Yeah.
and then write it in terms of n
Yeah.
equal 2 language.
Yeah. Yeah.
Some specific case of it.
Yeah.
Yeah.
And that's why I was saying that we turn off. There are some the charges of the gauge fields that appear in the gravitino multiplets will spoil that. So that's why we turn those to 0, and then we can do it. Yeah. But this is okay. Let me just mention this is what's left over of this duality invariance. The fact that the answer does not depend on the charges independently; it has to depend on this particular combination of the remaining charges that I didn't set to 0. So this is a particular case of the general form of this delta invariant for this restriction on the charges. Okay, maybe I won't erase that one. So let me roughly say how it goes. Okay, so let me see.
You had a lot of questions. It's okay. I mean, don't feel like you should panic.
Okay. Okay. No, it's okay. I don't want it to. Well, if everyone has to go, you can go. But yeah. So okay, let me write first. What is the measure of integration over the localization manifold? This measure you can think of as coming from the curvature of the localization manifold itself, but not from the one-loop determinants. Those are separate. And this is the answer. And I think this is another of things that would be nice to figure out better in this calculation, which is how to justify that this is the right measure to take. If you have presumably, let's say, a measure over, which you don't because, okay, supergravity. But if you had a measure over supergravity, then of all the supergravity fields, you would reduce it to the measure of the localization manifold. And then on that measure, then that will give you the right measure of integration. Well, we have some argument, and there has been some argument in the literature that this is the right reduction of the full measure on these localization modes, where well, the non-trivial part is the determinant of this imaginary part of the. Here, the indices means that you take two derivatives of the prepotential with respect to sigma and lambda, and the determinant is because this is a 16 by 16 matrix. This is the part that is harder to justify. The 1/c is simply from an assumption of ultra-locality of the measure. This just comes from the reduction of the volume of the space. All right. Something important is that this is some complicated function of the charges, but it has this dependence with C and this dependence with phi naught. And then here there is some. Let me put some function of Q and P that I can write down explicitly. But something important is that this function of Q and P is not U-duality invariant. It's not invariant under that T77. Okay. But then you have the one-loop determinants that, okay, I can tell you, you can ask me if you're interested, but the answer we got from the calculations with Luca and Samir is this. So this e to the k is the inverse of this ADS2 scale, so that's the only dimension-full parameter, that dimensionless parameter that appears in the problem. This factor of 4 is important. It's consistent with, if you do the calculation by saddle point, matches with this logarithmic correction to the entropy that's then computed. And this 1/c comes from the treatment of the zero modes. And okay, I can mention more about that, but this 1/c comes from the fact that on ADS2 cross S2 at 0 temperature or small temperatures, you have an infinite number of exactly zero modes, and that they come from the parametrizations of the boundary of ADS2. So you can act with diffeomorphisms that are normalizable, that produce normalizable fluctuations of the metric, but the diffeomorphism is not, and it acts on the boundary. And all these are zero modes, and you need to deal them carefully, and when you deal them carefully, you basically you realize that they're described by JT gravity, or the supersymmetric version of JT gravity, and that's responsible for this 1/c. Otherwise, everything else is independent of the orbifold parameter in the one determinant. But all right, but this is also a power of phi naught, roughly, to the 4. So this is a simple function of phi. So then the last thing I will say, or well, the last thing to write down is what is the action. Here we see we have this Q phi, and then we have this imaginary part of F. And the imaginary part of F is roughly, okay, let me write it, okay, like this. Oh, well, proportional, some factors, doesn't matter. So there is a term that is independent of the phi i's from 1 to 16, and it goes as 1/phi naught. And then there is another term that is quadratic on the phi i's from 1 to 16. So the way we do the calculation, and then the measure and the value determinants are all independent of all the phi i's. So then the point is that when you look at that formula for the answer for WC, you will see that all the integrals from 1 to 16 can be done explicitly because they are Gaussian integrals. So these things goes in the exponential, is quadratic on the phi i's from 1 to 16, so they're Gaussian. Something magic that happens is that when you do all these integrals, all the spurious dependence on charges that are not U-duality invariant combinations cancel, except in the action. And then you end up with an action that depends only on phi naught, which appears here as 1/phi naught. You have a term 1/phi naught, and you have a term that is linear in phi naught from this Q phi. That Q phi is Q0 phi 0 plus Q1 phi 1, etc. And this integral is precisely this integral over phi is precisely the integral representation of that Bessel function. And the powers of phi, this 4 and this 9, the powers of phi are the ones that you need. The one that tells you that the Bessel, I have here, is the one that tells you that it's this order. Yeah, 7/2. Yeah. Well, yeah, I don't know. Yeah, but if you look at the evaluation of the classical action after integrating out over phi, then, well, let me write it and then I'm done. Okay, this is the last equation I write. The integral representation of this. Okay, so basically sigma is a variable that is just a rescaling of phi naught, and the action is sigma plus pi square root delta over c squared divided by sigma. And this pi square root delta over c is the argument of the Bessel function, so it depends on your delta. And then if you track down the prefactors as a function of phi naught, then you'll get 9/2. And if you track down the factors of c, you'll get this c to the 9/2. So the integral over phi naught gives you an integral representation of this Bessel function. I guess I already kind of went over time. So okay, just to summarize, so this is the localization calculation for the index that reproduces this Rademacher expansion. Well, we already commented, but if you want to compute the partition function, you need to sum over other contributions, and we give some argument that none of them survive at 0 temperature. So then, in the black hole regime, the index should be the same as the degeneracy. Moreover, we have another argument in a paper with Luke and Murat that if you include wormholes in the integral that computes the statistics of this BPS spectrum, they all vanish, meaning that there is no factorization problem for this. There is no fluctuations of the number of BPS states. So then that explains why one can attempt to obtain an exact answer from this supergravity analysis. Okay, maybe I will finish with that. Thank you very much for your attention.
Question from our team. I guess there are a lot of questions.
Yeah.
I
Yeah.
mean,
Yeah.
but this is the only place where you're not where you're using extrinsic information that's not part of the gravitational passenger, right? Part where you decide which conical singularities to allow.
Yeah.
Is there no effective description of this in ND or
In what? Sorry, sorry, I couldn't hear you. In what?
in 10 dimensions, or really
In
I
10
guess it's like
okay.
a 3-dimensional space that you're effectively writing.
Yeah, it's 3-dimensional, but you have to combine ADS2 with the 11-dimensional circle.
Yeah, so
Yeah.
to make it look like a smooth geometry, it has to be 11-dimensional.
Yeah.
But can it, in 3D we get to have conical singularities by having like a point mass somewhere.
Mm-hmm.
Is there some matter content that can source this?
Yeah, so here we are thinking that all the matter that are not the massless degrees of freedom in 4D are integrated out, and they appear as higher derivative corrections that don't happen to not contribute in this calculation. Maybe what you're thinking, I think the only thing you could have left is maybe putting some d-branes, like assuming that your theory has some kind of d-brane that you can place somewhere and.
Membranes. I mean, those
Yeah.
are classical objects.
Yeah. So yeah, that's another question. So I think in this case those don't appear because of the amount of supersymmetry, but I think they might appear if you have less. For example, there is a similar expansion for the index of this 116 BPS black hole from n equals 4, super young Mills. And there you have contributions that near the horizon look like ADS2 cross a lot of other things. And there, if you want to reproduce the index of n equals 4, you have to add D3 branes wrapping like certain cycles that are at the horizon in ADS2, but wrapping some of the compact spaces that come from the 10 dimensions. But for this particular black hole, those don't appear. Yeah.
It's maybe we're saying that at this point, that result for n equal 4 for triangles is a guess.
Yeah.
That's how it's done, is that you take the index in the boundary theory, so you have no idea about the bulk, and you expand that index at large n, and you try to read off gravitational saddles in that expansion.
Yeah.
But that's not necessarily guaranteed to work.
Yeah.
One could actually perform the localization computation and see what happens.
Yeah. But in this n equals 8 calculation, you basically have controls of the gravitational path integral over everything except that step, right?
Yeah.
Except this one step
Yeah.
where you admit these seemingly singular
Yeah.
contributions.
Well, they're
Yeah.
seemingly singular from 4D,
Yeah.
but if you, as Joaquim said,
Or from 10D, right? You really need
For
the
10.
11th.
Yeah.
yeah.
Well, but the problem, but you could say that from 11, just to mention that it's even a little bit worse, that 11D is only accurate at strong string coupling. So I don't know if you can even use that picture at small string coupling from 10D.
So
So
you're really using some kind of string duality.
yeah.
Yeah, it would be nice to.
Yeah. But I don't say it to like complain. I think it's a good thing because then you can use, like for example, in n equals 4 case, you can use the n equals 4 to try to use it to explore what are the rules in the gravity path integral of what you should include or not, and try to understand.
I'm
Yeah.
trying to understand if you can
From-
come up with a definition of the gravity path integral
Yeah.
that somehow is plausible,
Hmm.
that would have told you to include these things.
Yeah.
You know, where you never had to leave your, again, my mindset is just like, could you have done this, you know, without inventing string theory first?
Hmm.
And what's, you know, interesting is that you're doing almost everything here
Yeah. Yeah.
without using string theory at all.
No, I agree. Yeah, I think that's the main step where we need some input about the fact that we need to include that, and yeah. I agree with you. I just don't know right now what the answer to that is. But I agree that would be nice.
So in 10 dimensions, that thing has a delta function of curvature for Ricci scalar or something like that?
Yeah, yeah. But it also has a delta function of this zero gauge field, and if you go to 11D, they kind of those two singularities cancel somehow. But I don't understand from a 10D perspective. Yeah. Yeah, but another question is also, so we didn't do n equals 4, so you can do compactifications, not on T6, but on some other Calabi-Gauss, 3-4 Calabi-Gauss, and then you end up with less supersymmetry in 4D. And then you also have other, then you can have more contributions that would be probably harder to argue, but I think that's the thing to do here, like to try to find the rules in gravity without talking about string theory, or without knowing the answer. I mean, it's hard because we know the answer, but like try to forget that we know the answer and try to find the right rules.
Yeah,
That's the
sort of reverse engineer.
yeah.
Like the way you did do the measure, right?
Yeah.
It's kind of simple. I mean, you don't know how to derive it from first principles, but
Yeah.
it's simple enough and it's fine. It works.
Yeah.
It's typically the case kind of when you know the kind of
Mm-hmm.
the right answer in this case,
Yeah.
and then you including this and got the right answer, probably this is the right thing to do.
Yeah.
Same for replica one more.
Mm-hmm.
You want to get
Yeah.
consistent with unitarity,
Mm-hmm.
because you could claim that we should not include any of those things,
Mm-hmm.
but doing that
Yeah.
to get the right answer.
Yeah.
And if you go to more less and less symmetric system like QCD, like
Mm-hmm.
instanton, you could argue that this,
Mm-hmm.
whether you include this,
Yeah.
because
Yeah.
of inclusion you have a strong CD problem. If you
Mhm.
don't include
I
it,
see.
that's better, but
Yeah.
then you have yet a prime right, problem. And all these things you just
There's another thing with the wormholes. I don't know, maybe it's actually the same. I mean, if there's only a countable set of candidates like this,
Mm-hmm.
that you can for each decide whether to include or not include, then I would say, okay, maybe that's kind of all right. You're just figuring out what the rules are. Maybe you can somehow
Mm-hmm.
define some rules to tell you to include these and not others.
Yeah.
I'm a bit worried that you might have to worry about putting conical singularities all over the place.
Mm-hmm.
but
Yeah.
my comment is that even
Yeah.
in QCD,
Yeah.
we're using, apparently to me,
Yeah.
you know, like from experimental data that we have to include this
Instantly.
instanton because yet a prime has a mass.
Yeah.
And deriving which, like this topological thing to include or not,
Mm-hmm.
is not easy thing.
Yeah.
Maybe this is a highly symmetric sectors and
Yeah.
supersymmetric sector. You might be able to determine top down that this
Yeah.
should be included or not.
Mm-hmm.
But in other places in physics,
Yeah. Yeah.
the pattern is that
Yeah.
you have
Well,
to,
in at least people did localization on gauge theories with n equals 2, and then you have a lot of instantons that then you have to include, like in these Preston calculations.
have to include
You have to include them to get the right
yeah,
answer.
So that's what
Okay.
I'm saying. Yeah.
Okay.
That's what I'm saying. Like,
Yeah.
Like this duality must be true, or
Yeah.
this has to be true, or this, yeah.
Yeah.
Sometimes it's very
Yeah, so here maybe it's a little better because in some cases we have the exact answer, but I think here what it means to get the right answer is to get an integer, so that you can have an interpretation of and that's very constraining. Yeah, yeah,
But it needs something
Yeah.
typically.
yeah, yeah. Like here, if you pick only this equals 1, you definitely don't get anything that you can interpret as counting anything. Yeah.
You don't really need things here, as you said. Like,
Yeah.
you just say, oh, this has to be integer. Maybe not. something, but
Yeah.
typically.
But that, yeah, but there is that's not put in string theory, maybe put in holography. So maybe it depends on whether you can have holography without string theory, or I don't know.
But that's, you're counting number of independent states, so must be integer. That's.
Yeah.
Oh yeah.
No, but you're assuming that the black you're
assuming.
you're assuming that the black hole is described by a quantum system. So that didn't.
Entropy was what derived kind of by semi-classical analysis, and then taking that very seriously,
Yeah.
saying that the number of state must be independent state must be integer, and then you use that as guiding principle.
Yeah, something like that.
Then you may skip string.
Yeah, yeah,
String theory.
yeah. That's yeah. Okay.